So now let's dive in. Now that we talked about ensemble models, let's dive into boosting more generally, and then a specific example of a boosting algorithm. So think about a learning problem where we take some data, we learn a classifier which gives us some output f of x, and we use it to predict on some data. So we say that y hat is the sign of f of x. So if we take some data and we try to make a prediction, we might learn, say, a decision stump. And so let's say you decide to split on income. We look at folks with income greater than 100,000, folks with income less than 100,000. And how do we learn the actual predictions that we make? Well, we look at the rows of our data, the rows where the income was greater than 100,000. And we see that for those, 3 were safe loans and 1 was a risky loan. So we're going to predict y hat equals safe. Now, if we look at incomes of less than 100,000, we'll see that we have 4 safe and 3 risky. So again, we predict safe. So both sides we're going to predict safe. And so it turns out that we do this first decision stump. Seems okay, but it doesn't seem great on the data. And so the decision stump wasn't enough to capture the information we needed on the data. So what boosting will do is take that decision stump, evaluate it, look at how well it's doing on our data, and learn a next decision stump, a next weak classifier. And that next weak classifier is going to focus on the data points where the first one was bad. So in other words, this is a very important point. In other words, we're going to look at where we're making mistakes so far, and we're going to increase, see the proportion or the impact or how much we care about the points where we've made mistakes. And we learn another classifier that takes care of the points where we've made mistakes, and then we learn another one, and eventually, as we'll see, we'll actually converge to a great classifier. What does it mean to learn the data points where we made mistakes? What it means is that we're going to assign a weight, alpha I, which is a positive number, to every data point in our data set. And that weight, when it's higher, it means that data point is more important. So you can imagine a learning problem where we have data, not just like we've done so far in this course, but we have data with weights associated with it. And now we're going to learn from weighted data. What does it mean to learn from weighted data? The way to think about it is that those alpha i's correspond to kind of the data points counting more than one time if it's greater than 1. So for example, if alpha I is 2, you can think about it as that data point is counting twice. If that alpha I was half, you can think about it as data point counting half of a data point. But everything in your learning algorithm stays exactly the same. It's just that you, instead of counting data points, we count the weights of data points. Let's see what happens in our decision stump approach. So we had that first decision stump. It was not great, especially for folks with low income. And so we learned these weights, which are higher for the places where we've made mistakes. And now we learn a new decision stump. Let's say again we split on incomes, again, greater than 100,000, less than 100,000. But when we look at the classifications decisions that we make, for greater than 100,000, what we do is we sum the weights of the data points that were risky and the income was greater than 100,000. So in this case, we're summing 0.5, 1.2, 0.5, 0.8, and 0.7, which adds up to 2. And then for the risky ones, it's 1.2. And so we're going to make a prediction that y hat is safe. So it's the weighted sum of the data points. For income less than 100,000, same kind of idea. We'll go through our data points, we'll look at the ones that were risky and the ones that were safe, and sum up the weight of those. And we see the total weight of risky loans 6.5. The total weight of safe loans was 3. So we're going to predict y hat is risky. So this decision stump is now going to be a bit better. So we're going to combine this one with the previous one and others until we create this ensemble classifier. Now, this idea of learning from weighted data is not just about decision stumps. It turns out that most machine learning algorithms accept weighted data. So I'm going to show you very briefly what happens if you're doing logistic regression and you have weighted data. So if you look at the equation on the bottom here, that's exactly the equation of logistic regression's derivative or the update function that we do. This is the thing that you would implement if you learn a logistic regression model. Now you say, oh, I have this weighted data, I have to re-implement everything from scratch. Oh my God, oh my God, oh my God. And it turns out that it's very simple. If you look at the middle of the equation, we have the sum over data points over here. And now, instead of just summing over data points, we're just going to weigh the contribution of each data point. So we just add that weight alpha I to each term in the sum, and we're done. We now have logistic regression that learns from weighted data. So we showed you 2 examples, decision stumps and logistic regression, but in general, it's quite easy to learn from weighted data. So boosting can be viewed as a greedy algorithm for learning an ensemble from data. We train the first classifier, let's say f1 of x, from data, and if you just have f1 of x, you just predict the sign of f1 to be your output of y hat. Now, then you reweight your data by weighting more data points where we made mistakes, where f1 makes mistakes. And now we run another classifier, f2, and we learn the coefficients for each one of these classifiers. And now our prediction, if we just do 2 steps of this, is w hat 1 f1 plus w hat 2 f2. And the sign of that is y hat. So that is kind of the idea of boosting. Keep adding new classifiers, learning the weights, optimizing the weights to focus on more difficult data points, and then learning the coefficients between different classifiers.